Welcome to 24 Hours of Past SQL Server 2014. We're excited you could join us for Jos den Bruin's session on SQL Server 2014 In-Memory OLTP for database developers. This set 24 Hours of Past event consists of 24 consecutive live webcasts. These recordings of the sessions will be available next week at www.24hoursofpast.com. My name is Ben DeBoe and I'm a partner at SQL HCA, where we focus on building mission-critical systems. And I have a few quick introduction slides before I hand it over to Jos for his presentation. We'll speak for the next 40 to 45 minutes, then we'll move into Q&A where you can ask them any questions that you may have. Next slide. For technical assistance, if you're having any issues, just raise your hand, the hand icon on the right side of your screen, and someone will assist you. To maximize your screen, use the Zoom button located on the top right presentation window. Feel free to enter the questions in the Q&A field at any time. The questions pane is located on the right side of your screen. Once we get to the Q&A portion of the session, I'll read off your questions to the speaker. Since all attendees are muted, you'll need to submit your questions by typing in the Q&A field. Note that there will be a short evaluation at the end of your session, and your feedback is important to us, so take some time to complete it. It'll show up on your screen after we're done. And I'd like to take a moment to thank our event sponsor, Microsoft, who is one of our global sponsors. The staging of 24 Hours of Past would not be possible without their support and dedication, and they are the reason that this event is available free of charge. Next, I'd like to bring your attention to the upcoming Past Summit. Taking place in Seattle, Washington from November 4th to the 7th, Past Summit 2014 will feature over 200 sessions with world-class SQL Server experts. Planned and presented by the SQL Server community for the SQL Server community, Past Summit is single-handedly the largest gathering of SQL Server and BI professionals. With over 5,000 attendees from all over the world, Past Summit is also a great place to network and meet face-to-face experts, peers, and MVPs. More importantly, Past Summit delivers on providing you with the answers to your SQL Server issues, along with the knowledge, strategies, and skills you need to stay ahead of the curve. Contact your local chapter for a discount code to save $150 off, and optimize that savings by registering before Friday, June 27th. To find out more about Past Summit, visit www.pastsummit.com. And now please allow me to present the speaker for the hour, Jos den Bruin. He's a senior program manager for SQL Server database systems. He's worked on the Hackathon project, bringing the In-Memory OLTP database technology to SQL Server. He's formerly an assistant professor, has a PhD in knowledge representation and semantic web technology. Jos, it's your turn.
Okay, thanks for the introduction, Ben. Welcome, everyone. Good morning, good evening, good afternoon, depending where you are. I'm in the Pacific Northwest, so for me it's morning, 9 a.m. And I will talk to you about In-Memory OLTP for database developers. So looking at the new In-Memory OLTP feature in SQL Server 2014, but mainly looking at the aspects that are relevant for the database developer. So I will be presenting a number of slides. We'll have a couple of demos. Then we will have some time for Q&A, but will probably be limited. Following this session, there will be an Ask Me Anything session about In-Memory OLTP, and I will also be there. So if you still have questions after the Q&A for this session, I will be available, and also Sunil, who presented about In-Memory OLTP for database administrators, I believe, earlier this morning. He will also be there. I also want to plug a new MSDN forum that we created, specifically for in-memory technologies that we have now in SQL Server 2014. So this is the SQL Server in-memory technologies forum on MSDN. There's a link in the resources slide in the deck for this session, so you can download and find it. But also, if you just go to the MSDN forums, look for SQL Server in-memory technologies. So in general, if you have any question about either in-memory OLTP, about our column store technology, this is the place to ask these questions. Also, people from the product team, including myself, including Sunil, including all the presenters that you are hearing or will hear at this past the past 24 event, they will be looking at this forum and answering your questions. Okay, let's go ahead here. So I want to do a brief recap of what the In-Memory OLTP feature is. So it is specifically a performance feature. That is what it brings. It does not bring any core new functionality. It brings performance. And it brings performance specifically for OLTP workloads, and it does that using in-memory database technology. Now, when we think about in-memory OLTP, we usually think about 4 core pillars. The first is memory optimized table and index structures. So we have completely new data structures for the memory optimized tables and the data as well as the indexes. So, for example, in terms of memory optimization, the base table rows are no longer organized in pages, structures. No, the row is now the atomic unit of storage, just accessible using a memory pointer, and indexes, they live only on memory. There's no copy of the indexes on disk. Then the second pillar is native compilation. So in order to speed up query execution beyond what SQL Server is capable of with traditional query execution, we compile T-SQL Server procedures and the query and procedural logic in these stored procedures. We compile them to native code, to machine code, in fact to a DLL, and we execute and a procedure execution corresponds to execution of a function in this DLL. Then also to achieve very high scaling for OLTP workloads, we designed all our data structures and algorithms to be completely latch and lock free. So we don't use any locking or latching to protect any physical data structures or for logical protection. Instead, we designed our algorithms such that physical consistency is guaranteed, and in terms of transaction isolation, we use a combination of multi-versioning and conflict detection to ensure transaction isolation. Now, I will talk a little bit more about what are the implications on your application for that in this session. And finally, this in-memory database technology is fully integrated into SQL Server. So you can have in one database, you can have both traditional disk-based tables as well as the new memory optimized tables. And you're not limited in the size of your database just by the size of your memory. This does, of course, limit the size of your memory optimized tables, but you can have as many disk-based tables as you want. So you can have a multi-terabyte database even if you have only, let's say, 256 gigabytes of memory. Plus also things like backup restore are always on, so fully integrated. Now, when we think about what do we think are the particular concerns for database developers for this technology? Well, first off, the tables and indexes. So how do you create them? What types of indexes do you use? Then how to access these tables. So we have 2 methods of accessing memory optimized tables. First, there's a traditional interpreted T-SQL, where you have your familiar ad hoc batches and your familiar classical stored procedures. You can use those, but you also have a new natively compiled stored procedures. So I will go into a bit of detail what are the implications and when to use what. And finally, because of the latch and lock free algorithm that we have, there are some implications on the behavior for transactions and particular transaction isolation. So we'll talk a little bit about what are the implications for your database application. So let's start with the memory optimized tables and indexes. So first, you will see a typical create table statement, a pretty simple one, table customer with 3 columns. And if you're familiar with T-SQL, many of these keywords will look pretty familiar to you. You have your create table statement, you have your column definitions with the data types, the not null, primary key constraints, etc. But there are a couple of things which are new for in-memory OLTP. I want to highlight those. So first there is the option to state that this is in fact a memory optimized table. Then there is the durability option. The default is schema and data, meaning that both your schema and your data are durable. So if your server falls over, your data is not lost. There's always a persistent copy on disk, and the transactions are fully logged. There's also the option to create a schema-only table, which we also sometimes call a non-durable table, where in fact the data will get lost on server restart or on always on failover. And those types of tables are only suitable for particular scenarios, such as session state or ETL scenarios, where either the data is transient or you still have a copy of the original data, which you can use if the server falls over. Then we have a new type of index, a hash index. And this is an index that's particularly suitable for point lookups. It's incredibly efficient for point lookups because you don't need to navigate through a complicated tree. You just go into your hash table to look up there, where's the row, and you go to your row right away. One important thing to keep in mind here is that you do need to specify a bucket count. The bucket count is the size of the hash table, and this is fixed. A hash index is always static, it will not change. That's for efficiency reasons, for performance reasons. We do have a recommendation. We want it usually to be between 1 and 2 times the number of unique index key values. However, if you overestimate it, it's usually fine. If it's 10 times more than the number of unique index key values, that is usually okay. Then the second type of index that we support on memory optimized tables is a non-clustered index. It is very similar to a traditional B-tree non-clustered index, although the data structure underneath is a bit different because it is memory optimized and also completely log and latch free. Then aside from tables, we also have memory optimized table types. So in fact, you can create a memory optimized table type and with that use memory optimized table variables throughout your application. And you don't even need to use memory optimized tables to be able to use these table types. And we have seen customers successfully use just table types and memory optimized table variables to reduce contention in TempDB. Because these table variables, like memory optimized tables, they live in the user database. They don't live in TempDB. And what happens under the hood when you create a memory optimized table, that's what this slide pretty much tries to outline. First, the user issues the create table DDL. Then we do a process of code generation and compilation. So we generate some C code, which is used for accessing a table, for cracking the rows, etc. So essentially, the table metadata is compiled into a DLL. So we don't, at runtime, when we access the table, we don't look at metadata and try to interpret that and try to figure out then what to do with the actual bytes. Instead, we use the table DLL to use both for seeks into the table as well as for cracking new rows, for retrieving the actual values from the columns. Then about indexes. So 2 key points about all the indexes on memory optimized tables are, 1, they exist only in memory. So there's no copy on disk. This means that, of course, they don't take up any space on disk, and also they're not reflected in the transaction log, which means that our transaction logging is more efficient. The second key thing is, and this is probably the most important from your application point of view, is that they do not contain any data rows. The data rows are in a separate table data structure, and you access them through the indexes. But the indexes, they only contain memory pointers to the data rows. They don't contain actual index keys or included columns or anything like that. So you don't have any duplication of data. And the indexes, because of this, because they all contain memory pointers to the base data rows, all the indexes are covering. So each index that you have, if you have, let's say, a table with 8 indexes, all 8 indexes will have pointers to the exact base data rows. So also no concept of include columns, no bookmark lookups, and this also one of the things where we say if you memory optimize is where one of the efficiency gains comes from. Now the two types of indexes that we have, non-clustered index and hash index. So first the non-clustered index. This is kind of the easier, more versatile index, whereas the hash index is more targeted and more optimized, but not as easy to use. So the non-clustered index, you can just declare a non-clustered index. You don't need to specify any options. It is particularly optimized for range lookups, let's say a date range, let's say a week or a month of a year, or doing ordered scans. It supports searching on leading columns of the index key, and it supports point lookups as well, so you can search on a particular index key value. But hash indexes are more efficient for that. Now, on the other hand, if we look specifically at hash indexes, you need to specify this bucket count when you create it. We do have guidelines, but you do need to worry about it. And if you get it wrong, in particularly if you underestimate it, this can have serious consequences for your performance. So you need to get it right, otherwise your performance will definitely suffer. The hash indexes are made for point lookups. So if you need to do just point lookups, use hash indexes. Also, they cannot be used for searching on a subset of the index key because you always hash on the full index key. So if you have a multi-column index key, you always need to specify values for all the columns if you want to search in this index. And also, you cannot use it for range or for ordered scans because it is a hash index, so the values are not in any order in the index. They're just hashed. Some considerations for indexes. So first, choosing hash versus non-clustered. We usually recommend using non-clustered indexes as a kind of safe baseline because they are the more versatile, support all the operations, easier to use. Then as a next step, when you start optimizing, you can use the hash index to optimize inserts and point lookups. So both inserts and point lookups are not as efficient with non-clustered indexes. And if you don't need any inequality seeks or other scans, then you can just use a hash index instead. And also one thing to keep in mind is you can have both indexes on the same columns. There are no restrictions there. In terms of the bucket count, so you want to have at least as many buckets as unique index key values. As I mentioned, oversizing usually okay. So if you have 10 times as many buckets as unique index key values, that's fine. In fact, it will, if you oversize, no matter how big the hash index is, that does not impact the performance of point lookups. It does impact the performance of full index scans, so you may want to look out for that. And if you have a lot of duplicates, we recommend to use non-clustered index instead because hash indexes don't handle duplicates very well. Finally, when thinking about picking an index key for a hash index, you need to keep in mind that they don't support seek on a subset of index key columns. So when you migrate an existing table with an existing non-clustered index and you think you need to do only point lookup, so you migrate to hash, make sure that whenever you want to search, you always have all the index key columns available. Okay, so now let me switch to a short demo. Let's hope it's going to show up. Yes. So what I'm going to do here is I will first go ahead and create myself a new database. I'm going to enable the database for In-Memory OLTP by adding memory optimized data file group and adding a container to this file group. This is in fact a file stream container. So this is now done. What I'm also going to do is set this database option, memory optimized elevate to snapshot, and this automatically maps the recommitted isolation level to snapshot because that is the basic isolation level support for memory optimized tables. A little bit more detail about that later on. Okay, now let me go ahead and connect to this database. So the table I'm going to create now is simple sales orders table with 3 columns: order ID, date, status, and we have 2 indexes: first primary key index and order ID, and then a non-clustered index and order date. I pick here a non-clustered index, because probably we'll want to do range scans on the order date. Okay. Now we can look at the catalogs, and we can see that also if you query sys.tables, we have the new options are just available in the existing catalog views, so we extended those. So sys.tables you can find is memory optimized, durability, and durability description. So let me now go ahead and insert some sample data. So IDs 1, 2, 3, 4, 5 with some dates, and now I'm going to update stats. So we do support auto create of statistics on memory optimized tables, but we don't support auto update. So after you do data load, you should always update the statistics in memory optimized tables. Now with the hash index supports and is targeted towards point lookups. So what I'm going to do is a point lookup now using my hash index. So I'm going to select the row with order ID. And I expect to be doing a point lookup into my hash index. And indeed the query returns the expected result. And we can look at the query plan for this. So, okay, let me see if it's going to show up. So we have here a non-clustered hash index seek, as you can see. So this is an index seek into the hash index, as expected. Okay. Now I can now try to do a range lookup. So what I'm trying to do now is select all the orders with order date, order ID actually greater than 2, and the returns expected results, of course. But if we now look at the query plan, we can see that we have a full index scan followed by a filter. And if we look at the filter predicate, we see that it is an inequality predicate. So in this case, I could not use the hash index to do an inequality search. Instead, I was doing a full index scan followed by a filter. So no, that is sufficient. And if I do a sort, okay, I can ask for order by order ID, and then the results return as expected. But again, if I look at the query plan, we can see here what we have is a full index scan followed by a sort, and we can see a sort has cost 99% of the total operation. If this index would have been in sorted order, I wouldn't have needed the sort operator. So for these types of operations, those use a hash index. Use the hash index for point lookups. Now I'm going to do the same style of operations with my non-clustered index on order date. Remember, I have an index on non-clustered index on order date, so I can do a point lookup on order date, and this query results return as expected. And we can have a look at the query plan, and we see indeed we have an index seek into the non-clustered index. And let's look at the range scan. So I'm going to add all the orders with order date greater or equal January 1st, 2013. Query results return as expected, of course. And let's look at the query plan. And what we see here is an index seek in a non-clustered index, and we see the seek predicate here is an inequality predicate. So this means that that we are only scanning the relevant part of the index. We are seeking to find the value that we're looking for, 2013, January 1st, and scanning the index from there. Similarly with sort order, so let's look for the orders ordered by order date. You can run the query, returns as expected. Now let's look at the query plan. And what we can see here is we only have an index scan. We don't have a sort operator. And we don't need the sort operator because the data is already in the order that we need. So if you need this type of sort order, or you need any inequality searches, use non-clustered indexes. Okay. Now let's go back. So the script for these demos that I have are all in the notes. So the next thing I want to talk about is how to access these memory optimized tables. So first I want to start with the new natively compiled stored procedures, which are the most efficient way for accessing memory optimized tables. So this is a typical create procedure statement, and it has all the required options for natively compiled stored procedures. And when you see here this comment insert T-SQL here, that's just plain old Transact-SQL that you use in these procedures. I just want to talk through all these options that we have here. So first, the option native compilation tells you that this procedure is in fact natively compiled. Then we require natively compiled stored procedures to be schema bound, because we cannot have some table disappearing underneath us when this procedure exists, because the procedure DLL is tightly integrated with the table DLL, just for performance reasons. Then also we require you to specify the execution context, so we require you to specify under which user this procedure is going to execute, because we don't want to do permissions checks every time a procedure is executed. Then we have a new concept of an atomic block. An atomic block creates a transaction if you don't have one yet. Otherwise, it creates a save point in a running transaction. So you no longer need to deal with begin, tran, commit, rollback. No, it's just an atomic block, and you know either all of it succeeds or all of it fails. And then the session settings are fixed at create time. So we bake the session settings into the DLL. We don't want to interpret those at runtime. There are a number of options you can set, such as the ones shown here, transaction isolation level, language, and a few others. And others we pick the default for you. For example, ANSI nulls are always enabled. Procedure creation looks under the hood somewhat similar to table creation. So you initiate the create procedure DDL, and under the hood we do code generation, compilation, create the DLL, load it into memory, hook it up to the SQL Server process. One particular thing you do want to keep in mind here is that we do have a step of query optimization. So we optimize all the queries when we create the procedure. Whereas with traditional stored procedures, they're optimized on first execution. But with memory optimized tables, natively compiled stored procedures, the procedure is optimized when the procedure is created. So you need to make sure the stats are up to date when you create the procedure. And in terms of when to use what and the trade-offs, so natively compiled stored procedures first. Things to keep in mind is that you can access only memory optimized tables, but they are the most performant way to access these memory optimized tables, and there are some limitations in the T-SQL service area because we do this code generation and compilation. Essentially, we need to implement every query operator anew. So, like the nested loops join operator, we need to create a new implementation of that. In the SQL operator, new implementation of that, etc. So we have some limitations. I've later in the deck a list with most noteworthy limitations. When you look at interpreted T-SQL access, this is your traditional T-SQL statements, your ad hoc batches, your traditional stored procedures. You can access both memory optimized and disk-based tables. So you can even have joins across them in the same query. But it is a less performant way to access the tables and to run queries. But we don't have really significant limitations. You can use virtually the full T-SQL service area in that mode. in terms of when you want to use the one or the other. Native procs, especially for OLTP-style operations, which process a fairly limited number of rows, where you have typical characteristics of doing a lot of index seeks, nested loops joins, and you'll want to use them for your most performance-critical business logic. Then in terms of interpreted T-SQL, you want to use those for particularly ad hoc queries, as well as reporting style queries, which process a large number of rows using, for example, hash joins, hash aggregation, and also if the service area you need, the query operators you need, are not available inside native procs. Have a brief demo. And what I want to show is in this demo, essentially a little bit of performance difference between different modes of accessing these tables. So what I'm going to do is I'm going to use my same table, sales orders. I'm going to insert 1,000,000 rows. We have a loop here in a traditional T-SQL. I have here an ad hoc batch that is going to insert these rows for me. And this is running and running. And this takes like a couple of seconds. What we see here in this case, this took about 7 seconds. I'm not sure if you can see it on the screen there. My Zoom is not working that well at the moment, but it's about 7 seconds. And we can see the data is there, as expected, in no particular order, even though I was inserting in increasing order with order ID. It's a hash index, so they are essentially inserted at random. Now let me clean this up. Now I'm going to do the exact same work inside a natively compiled stored procedure. So I have here a natively compiled stored procedure that has the exact same logic, that has also the 1,000,000 inserts. Because this is a native proc with an atomic block, I don't need to bother with the create transaction or with the commit. So let me go ahead and create this procedure, and then I'm going to execute this procedure. And as we can see, this took all of 2 seconds. So there's some significant performance difference. And the big difference comes from the fact I'm doing all this work inside the natively compiled stored procedure. Now, the final thing I want to show here is that the fact that you are just using a native proc does not necessarily mean things go faster. So what I'm going to do now is I'm going to create a natively compiled stored procedure that does a single row insert. So it takes a bunch of parameters and inserts a single row inside this procedure. And what I'm going to do now is in interpreted T-SQL, I have a loop that executes this procedure 1,000,000 times. And now the thing is that this loop is being executed in interpreted T-SQL. So loop is not natively compiled. It's only the insert logic that's natively compiled. And insert is very small in terms of code path. It's a very simple, fairly simple operation. And what we can indeed see here, I don't know if you can see it on the screen, but it took about 13 seconds. So this is indeed even slower than when I was running this as an interpreted T-SQL batch. So main point here is that for if you just do a simple operation like an insert or just singleton insert or singleton select, you don't get a lot of benefits from native compilation. You do get a lot of benefit if you do a bit more, if you have like a couple of statements or you manipulate a couple more rows, then you will get some significant performance increase. Okay, let's go back to the slides. Then transactions. Transactions on memory optimized tables, that's a pretty big topic because essentially this is completely new transaction semantics that's quite different from traditional transactions in SQL Server. But I will because limited time, I just want to highlight some kind of main components. So first, so transactions concurrency control, that's what we're usually talking about in the sense of transactions. So because the whole thing with transactions becomes interesting when you have multiple transactions running concurrently in the system, right? And then you need to worry about like how they interfere with each other, because what we see is these days servers have lots of cores. You would have one. You might have a 2-socket machine. Each socket has like 12 physical cores. So you might have hyper-threading. So you might have 48 cores in your mid-range server. So you could have 48 transactions running at the same time in your system. And then the question is, okay, you're trying to access the same data. Are we going to interfere or not? Right. So, and we, of course, we want as little interference as possible. We want to have a maximum scaling. And in fact, we managed to achieve pretty much linear scaling, at least for 2-socket and most 4-socket workloads as well. And there are two main pillars in In-Memory OLTP concurrency control. First off, it is multi-versioned. So with multi-versioning, you can already get rid of the conflict between readers and writers, because if you update a row, you just write a new version of this row, and if someone wants to read that row at the same time, they can just read the old version. Right? And the multi-versioning with memory optimized tables is built into the core table data structure. So we have no things in TempDB or anything. It's just part of the core data structure. And then with this multi-versioning comes also the snapshot-based transaction isolation. So transaction isolation with memory optimized tables is always snapshot-based. In your transaction, you will always see the snapshot as of the beginning of the transaction. And this holds for all isolation levels, snapshots, repeatable read, as well as serializable. And again, we don't use TempDB at all for these snapshots. Because again, they are built into the memory optimized data structures. So you don't even need to enable the database option for snapshots. No, it's always multi-versioned. Then also it is optimistic, because we don't want any locks, we don't want any latches. Also, we want to minimize context switches. So we don't want any waiting in the system. We don't want one transaction to block another transaction. So what we say is we are optimistic, and we are going to assume that everything is going to succeed. There are not going to be any conflicts, which means I don't need to take a lock, because taking a lock is a more pessimistic thing. You take a lock when you are afraid that someone else will touch your data, will touch your row. But we're saying, okay, we assume it's not going to be the case. And for the cases where there are conflicts, we detect those conflicts, right? And then we fail the transaction that's causing the conflicts. And in practice, we're seeing that with most workloads, these transactions are rare. If you think, for example, about bank accounts, right, which is typically used in OLTP examples for transaction isolation, you want to have like 2 updates to a bank account to be consistent. But in practice, how often do you actually update the same account at the same time? How often do you have that one person deposits 2 amounts to the same account at the exact same time? This is very rare. So what we do is, if conflict does occur, we fail this transaction. This transaction will need to retry. But in practice, as I said, we don't see a lot of those. Also because we don't have any locks, we don't have any deadlocks. So the isolation levels we support. Our basic isolation level for memory optimized tables is snapshots. So, with snapshots, reads are always consistent as the start of the transaction, because you're reading from that snapshot. Writes are always consistent. Because if there's a potential inconsistency, we fail the transaction. Then what we usually recommend, especially for existing applications, is to use this database option, memory optimized elevate to snapshot. What it does is, if you have a read committed transaction, so if you have, let's say, transaction isolation level set to read committed in the session level, and you just say begin tran, you start accessing memory optimized tables from interpreted T-SQL, then we just interpret it as being snapshots, so you don't need to use any particular table hints. So we've seen if you use this option, you will limit the changes you need to make in an existing app. Repeatable read, we support that. Of course, the guarantee you get from repeatable read is that if you would read the same rows at the end of the transaction, the state of the database has not changed, so you read the same version. Now, one important thing to keep in mind is that we don't use logs for this guarantee. Instead, we verify at the end of the transaction whether this assumption holds or not. If it does not hold, you will need to retry the transaction. Similarly, for serializable, this is the additional guarantee that there are no phantom rows. But again, we check at the end of the transaction if there are phantom rows. If so, you will need to retry the transaction. So this is like kind of simple visualization of a write conflict. So in this scenario, we have two transactions, transaction 1 and transaction 2, and they both attempt to update the same row. That's where C2 equals 1, 2, 3. Right. Now transaction, they both begin at some point, but it doesn't really matter when they begin. What matters in this case is which transaction updates first. So in this case, transaction 2 updates the row first. It marks the row as this is being updated. Transaction 1 comes in and sees, oh, this row has already been updated, so now I cannot update it anymore. So I will need to fail, and the client will need to retry the transaction. So always in this case, always the first writer wins. So let me just get to the demo because we don't have that much time left. So what I want to do here is I want to contrast the behavior with traditional disk-based tables, read committed isolation and locking, with the behavior with snapshot isolation for memory optimized tables. So first I'm going to create a sales orders disk table. So this is a traditional disk-based table that has the same schema as my original table. Oh, and I see I have a syntax error here that I should correct, and I just did. Okay, there we go. And I'm going to insert the same rows in both tables. So again, my sales orders table, that was my memory optimized table, and sales orders disk is my disk-based table. I'm going to insert here rows 1 and 2. So what I'm going to do now is first start a transaction and update row 1 in the disk-based table. So what happens now is that I take a look on this row 1 because I'm updating it, so I cannot allow anyone to read it anymore. So if in my second transaction, my second session, I attempt to read from this row, you will see this blocking behavior. So it is now waiting for this lock to be released. Once it is released, I can finally continue. So what I'm going to do now is commit my first transaction. So now I release this lock, and what we can see here is that the query results for this select statement now finally return. And we see here the updated order status 2. Right. Now if I'm going to do the same thing for memory optimized table, I'm going to begin a transaction and update row 1 in my memory optimized table. Now what happens now is I don't update the row in place, no, I write a new row version. So the old row version is still available to read by anyone. So if I now read this row version from my second session, we can see, hey, indeed, this returns immediately. But of course, I see here the older version because the original transaction has not yet committed. Now, if I attempt to update this row with a concurrent transaction, I'm now going to attempt to update my row 1. So this is now a write conflict. Right? So my first transaction has already updated this row. Now a second transaction comes in and attempts to update it. So what's going to happen? Okay, now this transaction is going to fail. The current transaction attempts to update a record that has already been updated. So now I would need to retry this. So my first transaction, let me go ahead and commit it. And what we can see here is that indeed my new row version, my new version is available, or the status 2. Okay. Then, well, I'm going to skip a little bit ahead because I don't have too much time here. What I want to show you is a case where you get a deadlock when you use read committed with locking, and you don't get a deadlock, and everything succeeds if you use snapshot isolation memory optimized tables. So what I'm going to do is I'm going to first with the disk-based table using read committed isolation level. And I use here these table hints to emphasize the fact that I'm using this isolation level. So I'm going to begin a transaction and update row 1. So because I'm using read committed, this takes a lock to protect this this row. Right? So nobody can read it now. Now my transaction B, I'm going to update row 2. So transaction B takes a lock on row 2. Now with my transaction A, I try to read row 2 and that commit. Now there is a lock on row 2, so I cannot read it. So I'm now blocked behind this lock that transaction B has. So it will now just keep waiting. Now in transaction B, what I want to do is read row 1. But remember that transaction A took a lock on row 1. So when I start running this, we see this starts to block, and we'll just wait. And this is a typical deadlock situation because you have these two transactions waiting for each other to release locks before they can continue, and they cannot continue until these locks are released. So SQL Server deadlock detection comes in and detects there is a deadlock, and we can see one of them is chosen as a victim. In this case, the second one. Now let's see what happens in a similar situation with memory optimized table. So I'm going to begin transaction A, update row 1, begin transaction B, update row 2, and then I'm going to read row 2 and commit my transaction A. This succeeds, and this is of course the older version of the row. And I'm going to also, in my transaction B, read row 1 and then commit. And in fact, this also succeeds. But again, keep in mind I was reading the older version of the row because this is snapshot isolation. But my transaction goes through and commits, so no deadlocks in this case. Okay, let's continue here. So that is that's just a flavor of of the new transaction semantics and the implications on your application. And the main thing to keep in mind there is are the right conflicts. So that is something you always need to be mindful of whenever you have an update or a delete. It could always happen that there is a conflict with another update or delete, and you will need to retry this transaction. So you will need to retry logic either in a wrapper stored procedure or you need to build into your client app. So this is the limitation slide. What I want to show with this slide is the main surface area limitations that we have in SQL Server 2014. So again, these are completely new data structures, new algorithms. Native compilation is completely new, essentially completely new implementation of query execution. So we were not able to support all the features that SQL Server has built up over the last 20 years because we had a limited amount of time, of course, and we wanted to get this release out to you. So these are the main things we want to call out, you want to keep in mind. Also another thing to keep in mind is that we continue to actively invest in In-Memory OLTP, and the next release of SQL Server, a lot of these limitations will go away. So for tables, we don't support any triggers, so no DTL or DML triggers. In terms of data types, no log types, so no nvarchar max or varchar max or binary max, and also no exotic types like XML types, CLR or spatial. In terms of constraints, no foreign key, no check constraints, but we do support default constraints. We don't support schema changes, so no add or remove column. If you need to do that, you need to drop and recreate the table. Also, we consider add or remove an index as a schema change because the index structures are tightly integrated with the table data structures as well as with the table DLL. So if you need to add or remove an index, you need to drop and recreate the table. In terms of natively compiled stored procedures, we do support the usual imperative logic as well as error handling, so things like if, while, begin, and try, catch. We support those things. We don't. In terms of queries, we do support the very basics like group by aggregation, joins, particular inner joins, the where clause with and. But there are definitely some limitations that can have an impact on how easy it is to migrate your stored procedures. So, in particular, no outer join, no distincts, no or, no subqueries, no case. And everybody's always wondering, why don't you support or? It's very basic. Well, we do agree it's very basic. It's just a whole lot of work. And we know it's high on the list for us to implement for the next release. So to briefly recap, we have these new memory optimized tables and memory optimized indexes. They're completely new types of structures optimized for in-memory data access. The tables are natively compiled on create, and we have this new type of index, the hash index. And besides the hash index, we also have the non-clustered index, and you'll need to think a little bit about which one you want to use in your app. We usually recommend non-clustered index as the kind of safe baseline to start with. In terms of accessing memory optimized tables from your app, we have the new natively compiled stored procedures, and the interface actually for calling these natively compiled stored procedures is the same as for traditional stored procedures. So you can use the same clients, the same SQL clients as you did before, and we support RPC execution, we support prepared execution, and of course execution from T-SQL as well. We also support table value parameters for that matter. And natively compiled stored procedures, they provide the best performance for where you in your queries, your search. And finally, for the transaction semantics, to ensure that writers don't block reader. The isolation is snapshot based always, so in your transaction you're reading always from as of the start of the transaction, and we don't have any locking. And if there are conflicts with concurrent transactions, we do conflict detection, and you need to retry the transaction if such a conflict occurs. I have here a bunch of links. You can download the deck, follow those links. The first link is the In-Memory Technologies forum that we just created, that I was just plugging. In particular, if you have any questions, any concerns, running into any trouble, or even you want to know how to get started, even if you have very basic questions, feel free to go to that forum, post there. Myself and other folks from the product team will be looking at the forum. So then it is time for questions.
Yes, one of the important questions is that the notes aren't saved on the PDF slide deck. So how, or will we be able to provide the scripts in a different method, and we'll just need to let people know when and where?
Yeah, I can send them to whoever. I don't know if there will be an option to download them from the website, but I'm sure we can figure it out.
Yes, yes. So the first question is, can I write a query that joins an in-memory table and a disk-based table together to receive some related data?
Yes, absolutely. That is fully supported. You can access both memory optimized tables and disk-based tables in the same query without limitations. You just cannot do it inside a natively compiled stored procedure, but in a traditional ad hoc batch or traditional stored procedure, you can do that without limitation, yes.
Does a new cardinality estimator work on in-memory tables related query plans as well?
Yes, it does. For memory optimized tables, we leverage the same query optimizer as for disk-based tables. We made some tweaks to make it aware of the characteristics of hash indexes as well as some of the performance characteristics so that it does the right cost estimation. But yes, the new cardinality estimator fully works with memory optimized tables.
And can you have a recursive native compiled stored procedure?
Can you have a recursive native compiled stored procedure? Well, if you're talking about recursive CTEs in native compiled stored procedure, that's not supported right now. Also, we don't yet support calling procedures from a native procedure, so you cannot nest native procedures. So we also don't support recursive calls. Though once we support call nested procedures, I'm not sure we would support the recursive scenario. So if you have specific concerns about a scenario, feel free to send me an email or post on the In-Memory Technologies forum and we can discuss further.
And can you have native compiled stored procedures within normal ones and vice versa?
Can you have native compiled stored procedures within normal ones?
I think they're talking about the in-memory store procedure or natively compiled store procedure versus the
It's about calling a natively compiled stored procedure from an interpreted procedure?
Yes.
Yes, this is supported, but not the other way around. So you can call a native proc from a non-native one, but you cannot call an interpreted proc from a native proc. The last one is not supported at the moment.
And does a in-memory table contain all the data in memory? If yes, then are there any recommendations on how much data they should contain or how to size that?
Yes, all the data in a memory optimized table is in memory, so you need to size your memory appropriately. Basically, you need to look at your data size, which is basically we have some calculations online, but it is the size. Essentially the size of your column data times some row overhead plus some row overhead, times the number of rows, and then we have a little bit of overhead for indexes as well, where especially if you use hash, the overhead is very limited. But you need to make sure you have enough memory, both for the data itself as well as for the query execution. And then the thing is also, one thing I want to remark about that is you have cases where you have a single table and it may not all fit in memory, but it's only part of the data is hot. So only part of the data you need to access frequently and frequently update it. So what you can do is just put part of the data in a memory optimized table and then have a disk-based table with the same schema, and you can do then some regular offloading. Like you can regularly say what is the cold data that is still in memory and move that to disk. And you can use a union all query for cases where you need to access data across two tables.
Okay, thank you. And that's enough time for today. And then thank you for your participation.
Yeah, thanks. So one reminder for the folks here, the next session will be In-Memory OLTP, Ask Me Anything, and I will also be there. So also for further questions, and also please go to the forum if you have any further questions.